Good morning, Astronomy 1020. In 1977, NASA launched a pair of spacecrafts called Voyager 1 and Voyager 2. And Voyager 1 and Voyager 2 were spacecrafts which were designed to do flybys of the outer solar system and pass by the gas giants Jupiter, Saturn, and in the case of Voyager 2, the spacecraft also flew by Uranus and Neptune as well. And after their mission was complete of surveying the gas giants, these spacecraft were flung out of the solar system into deep space to take as much data as they could about the conditions at the edge of the solar system, and then just to keep going forever as far as they could go into outer space. And because these would be the first two man-made spacecraft to leave the solar system, scientists decided that perhaps we should put a record of where these things came from. And when I say a record, a literal record, it's known as the Golden Record. And it contained a stylus and instructions for how to play it in pictographic form. And it had the greatest hits of Earth, waterfalls and bumblebees and people saying hello in all these different languages, and some cool pictorial instructions about what this was and how to play it, all mapped out to the size of a diatomic hydrogen atom. Well, I have my own version of the Voyager record to share with you guys, but unfortunately this one's not made of gold, it's made of brass. And this message isn't so much to any of you guys who I'm seeing here in front of me, it's to all those students who the only day they decided to do anything for this class was the day they decided to register. And after that, they just sort of punched out. I don't know why that was the one day they had it together, okay? But there were some people, and I don't think it was anyone here, thank goodness, who just didn't take my test. And some of them started taking the test and then just, I don't know, they just didn't finish it or something. But this message is my own Voyager message that's going past you guys, because you guys are present, and past some of the other trolls who are here too. And I don't think those people are going to hear this message, because clearly they didn't watch any of the other videos either. But just in case, even though the probability is similar to that of aliens encountering the Voyager 1 or 2 spacecrafts, maybe one day they'll hear this message, which is, all you got to do is show up. All you got to do is just be here and hang out with me, and things will go better for you. So you guys know that I talked about the test many, many times. It's in the syllabus. I don't know what else I could do, but it scared the willies out of me when I computed the midterm grades, just how many people didn't take it. And that terrifies me as an instructor. I don't know what to make of it. So if you're out there listening, space aliens, please come back to planet Earth, log into Astronomy 1020, find out what's going on. Okay, before we do our lecture today, which is an amazing lecture on the first part of the sun, I thought we could take a few moments just talking about how I computed your midterm grades. Did anyone check to see if they could view their midterm grade? Mariah, was it there? Could you guys see your projection?
How do I see that?
Yeah, it was there.
I think.
Yeah, I just checked it in the morning.
Cool.
You have to go to MyPCRI and you put in the semester you want, and it'll show you your grades.
Yeah, so Andrew, go to MyCCRI, and then you check, just like Mia said, I think there's a thing for viewing your midterm grades. I have a enter midterm grades. I'm guessing you guys have view midterm grades as your button, right? Something like that? Okay. I've got so much cool stuff to tell you about today, so I don't want to waste too much time on administration, but since you guys are probably concerned or curious about how your grade is computed, I want to unveil the curtain and show you the underworkings of the machinery in case this helps you in some way. So let me.
Well, you said you did some magic while computing it, like scaling or something.
There is a little bit of magic going on there, yeah, and I want to share that with you. Okay, hold on, my taskbar is like in the way. All right, here we go. Sorry. All right, so let me just erase this quick. And our test, by the way, while I'm erasing, how did you guys find the test? Did you find it was straightforward or like pretty brutal? I'd like to hear some of your feedbacks.
It was good. A lot of my brain went in every single other direction though.
Wait, I don't know where to go. I'm on the My Student tab and I don't see it.
It's a lot of
So when you go, when you're in My Student tab, you scroll down, and then you should see the midterm grades, but they will be probably from semester 1. So you choose Spring 2021.
Yeah, that's what I did, and nothing's showing up.
Well, I'll tell you what, Andy. Why don't I'm tempted to get bogged down in your computer issue, but why don't we wait at the end of class today? Because today will be a shorter than average class, and I'll maybe Vladimir will hang out with us at the end of class, and we'll help you find it. Okay? We can even do like a share screen thing.
All right.
Does that sound good?
I wouldn't be here. I have to leave early today.
Oh,
I have work.
nuts. Oh well.
I'll figure it out.
Yeah, you can do this. I believe in you. Okay. Let me lower my lights a little bit. It's kind of bright. Okay, so listen, guys. I know the test is long and brutal. The upside is you don't have to do it too often, right? So I've decided to make more horrible tests and less of them because tests are stressful. So I figure we just put all that stress into one big ball. We get it over with. It did amaze me that for some people, 3 days wasn't long enough. So I literally think if I gave you guys a month to do the test, I think some people would just take a month. At some point, it has to stop, right? Your midterm grade is computed in the following way, okay? So as you remember from your syllabus, homework is worth 25% of your grade, okay? Lab is worth 25% of your grade. The midterm is worth 25% of your grade. And what really matters is in the final grade, which is the one that will appear in your transcript, the final is also worth 1/4 of your grade. Now, here's the deal. I have points for homework, points for lab, and now I have points for midterm, but I don't know what this is going to be yet. I cannot simply take an average of these 3 percentages, and I bet you guys could figure out why. If I took an even average of homework, lab, and midterm, each of these would be weighted by 1/3, which math fans will know is 33%. And that will make your homeworks and your labs have a greater weighting than they will in the final. So it's not a good projection. Here's what I'm going to do. I presumed when I calculated your midterm grade that whatever you got for the midterm exam would be the same score that you got for the final. Now, that's not necessarily true. That's up to you, not so much up to me. But since I have no other data to work with, by the way, it does turn out that people tend to score within 5, usually 5, and sometimes within 10 points of their midterm grade. But people tend to be actually kind of consistent on that. And then I apply a gentle curve, which I want to explain to you. The good thing about my curve is that I've made it so that even if you don't do so hot on tests, you can totally get by in this class and pass with flying colors as long as you show up and you do the homeworks and labs with me. All right, that's the big takeaway. So for instance, let's imagine a random student named Joey, who I'm making up, okay? And let's say Joey is a person like one of you guys here on the screen who always hangs out and shows up to class and does their homework and lab like a good boy and girl. In that case, I think we had maybe 5 homeworks to work out of. So Joey would have done all of his homeworks the way I wanted him to do them. And it would be 125 out of 125 points. So he's got a 100% average for homework. Nice. And let's say he did all of his labs. I think there were 6 of them. So 60 out of 60 points means 100% on your lab score. And let's say Joey just did kind of average on the test, not so hot. Maybe let's say Joey got a 50%, okay? Now, I presumed for my midterm calculation that Joey would get a 50% on the final as well. And then I took the averages of these 4 numbers. You guys can see that this adds up to 3 out of a possible 4 points. So Joey's final midterm percentage, to the best of my ability to compute it, was a 75%. Okay, what does that mean for this class? Well, here's how I feel like, based on the difficulty of this class, the fact that many of you are not science majors and haven't had to do tricky problem sets before. This is what I think an appropriate scale is based on my experience in this course. I peg B- to a 65%, which is a very generous scale that I think gives everyone a buy-in here. And then I go in sort of 5-point increments from there. So a B would be pegged to 70% and above. B plus is anything 75% or above. A minus would be 80% and above. And then anything above 85% is an A. That gives us lots of wiggle room. On the other side, C plus is 60%. Now, we don't do C minus at CCRI, and I think that kind of gives me the right to extend C actually all the way past 55%, all the way down to 50%. And under that, that's when you start to enter some bad territory, right? So that's what I would consider bad territory. A D plus is 45%, a D is 40%, and EGADS. If you can't get more than 40% points in this class, then you have definitely earned an F. And luckily, that doesn't happen too often. That usually only happens when people are just flakes and just flake on everything. They flake on their homework, they flake on their labs, they flake on their midterm. The only thing they didn't flake on was the day they signed up for this course. On that day, the people had it together and nudged out someone who would have preferred to learn in this class, and that blows my mind. But whatever, I can't control the universe. Notice that Joey, who just did kind of so-so on the test, is still getting a bloody B plus in my class because Joey is not a flake and Joey shows up and does his homeworks and labs. That is so cool. That means that you don't have to be Albert Einstein Jr. to get a great respectable grade in this course. You just have to be a person who's willing to hang out with me and at least feign an interest in cool outer space stuff for a couple hours a week. All right, so I think that's a good deal if you ask me. You certainly would have to do more in another class. I hope this makes sense to you guys. Tegan, you know, hate to give what the kids call a clapback these days, but you know, this is why I'm so concerned, Tegan, about missing labs, because you're someone who does participate in the class, and I love you for it. But if you're going to participate in the class, you might as well turn those labs in, because I don't remember how you did on the exam, but you could see that having this to boost your grade is very, very helpful, right? So we're not going to miss any more labs, are we, Tegan? You're never going to do that again. Okay. Do you guys have any questions about this before we move on today? Because there might be some aspect of this that you're unsure about, or all makes sense, I guess. Yeah. Okay, cool. All right. Well, that took a little bit of time, but I thought it would be good for you guys to see the exact method in which your grade's being computed, and you can use that knowledge going forward. At this point, I consider you guys to have graduated from Baby Physics Academy. Yay! We can actually start talking about astronomical objects because you guys have the psychological machinery to go forward here and talk about some cool stuff in space. And you know what we're going to start with, since this is a class on stars? We're going to start with the sun, our star, the best star, the star that we know the most about. And I'm going to show you guys some really cool videos from the Solar Dynamics Observatory in just a moment. Oh, one more thing that I didn't think about. Today is a Thursday. Normally we have lecture and then we do a homework afterwards. I don't think I'll be able to lecture enough about the sun today for us to be ready to do the homework 6 on chapter 14. I don't think we're there. And remember how I skipped over lenses and telescopes last week? I was thinking it could be a fun little thing for us to do before spring break. Let's have lecture, and if you guys are cool with it, we'll do a lab today instead on telescope building. It's faster than doing a homework, and it's probably more fun because we get to play around with lenses. Everyone on board with that?
Yeah, I already did it.
You already did it, so you'll be able to punt. Actually, Andrew, you'll be able to leave early, but remember.
And catch up on my other thing.
Exactly, and I wanted to say something about that. You know how I normally close submissions for labs? Because it was a little bit confusing, what I did last week, where I suddenly went from lenses and telescopes to inverse square law, I think some people got confused. So I've left that lab open, Andrew. You'll see when you go to the lab tab, how do I get my...
Yeah, I saw it. I went under there today, as you told me.
Right. So over here on your lab tab, I want to let the whole class know that I've left open last week's lab a little bit extra longer because some people got confused. Some people were trying. So today I'm going to rename this Lab 7. I'll have to figure that out later. But we're, in fact, I better do that now before I forget, because I get forgetful sometimes. Come on, buddy. All right. So this lab for next week will be question mark for now. and we're going to make Lab 7 lenses and telescopes. This means we're diverting a little bit from the procedure from last semester. That could be, I understand. What did I just do? Okay, sorry about this administrative stuff, but I don't dare, oh, sorry. Okay, I'll get confused. All right, we'll all get confused. Anyways, so that sounds good to everyone. Doing a lab today instead of a homework? All right, cool. I think that'll be the best procedure.
Quick question.
Yeah.
So just to make sure, we didn't have to turn in the practice problems for the exam, right?
No, that was just to try to help you guys. That was not a required turn-in.
All right.
But I'm glad you asked, because someone asked in yesterday's class too. Okay, so let's get down to business and talk about the sun. A lot of what you're going to learn about today, a lot of the cool videos that I'm going to show you come from a legendary satellite called the Solar Dynamics Observatory. All I have to type into Google is SDO, and you can see the Solar Dynamics Observatory is the very first page that comes up here. What is it? It's a totally cool satellite that is basically a telescope that looks at a variety of different wavelengths of the electromagnetic spectrum. It's in orbit around Earth, and its job is just to constantly point towards the sun and continuously image the sun at all kinds of different wavelengths of the electromagnetic spectrum. So this is sort of an illustration of what the spacecraft looks like. It's in a polar orbit going around Earth, so it can constantly point towards the sun. It images in the visible, infrared, ultraviolet, and X-ray portions of the EM spectrum. It doesn't really do radio waves or gamma rays, because if you look at the black body curve for the sun, the flux in radio and the flux in gamma rays is very, very low. And it's actually kind of difficult to build those kinds of detectors in space. But it covers all the main portions of the EM spectrum where the sun is emitting most of its light. Not only that, guys, but it's imaging nonstop and takes some very cool movies. I want to show you something right from their webpage. This is an image of the sun at 193 angstroms. Do you guys know how many nanometers that is? Who's good at converting from angstroms to nanometers? Y'all probably forgot, huh?
Yeah, I don't remember.
An angstrom
Oh wait, is it like 1,000? No,
it's
100.
a tenth. An angstrom is a tenth of a nanometer.
Tenth.
So this is an image of the sun taken at 19 nanometers. Do you know what portion of the EM spectrum that's in? Let's see how well you've studied for your exams here.
Ultraviolet.
Yes. Yes, but it's close to the boundary of X-rays. Remember, it's 10 nanometers is the boundary between X-rays and UV. So very good, Vladimir, impressed. And look at the timestamp on this, guys. 2021, March 4th, today, at 1700 hours GMT, which Philemon knows from my 1010 class is 5 hours off from Providence, right? So if this was 17 o'clock, this was taken at 12:17. That's like,
oh, it's like 20 minutes ago.
Yeah, isn't that amazing, Vladimir?
Wait.
They're uploading pictures. This is what, and by the way, they're not, these are images of our sun today at all these different wavelengths. Every 20 minutes, it's dumping data here. And by the way, you can go to their movies section, and their daily movies are just mind-blowingly cool. If you browse the daily movie directory, let's go back a few years ago. What's your birthday month and day, Vladimir? Let's see what the sun was doing on your birthday in 2015.
December 16th.
All right, so let's go to December. Come on. Oh, and this is the, all right, these are the days. And this is the 16th. All right. So I happen to know that which one of these is usually pretty good. Usually these are pretty rad. Let's just click on see what the sun was up to. That's what the sun was doing in 2015 on your birthday. Pretty cool, right? You can now, I got a couple of these videos that I think are really wild. And the point of this is to kind of get you excited to talk about the sun and think about the sun. Let's start with this image here, F5, slide 3. If you could look at the sun at visible wavelengths at 4,500 angstroms, how many nanometers is that?
450.
Right. What color is that?
So 500 is green. No?
Yes.
So it's like, it should be closer to blue than orange. Because
Yeah.
doesn't orange have a longer wavelength?
Well, that's what I'm trying to get you to think about here. So, in fact, look at a better picture here. What color is 450 nanometers if you had to describe it with one word?
Plain blue.
Blue.
Is that the best you guys can do? I thought you guys.
Oh, indigo. Indigo, okay.
Indigo. This is indigo as the day is long, right? Okay, cool. So here's something to think about. They're imaging the sun at a narrow band filter, meaning they don't just let in all of the visible light, Roy G. Biv. They're letting in a narrow band around 450 nanometers. Basically, this is what the sun would look like at indigo light. So why the hell does it look yellow?
Because we're stupid?
Yes, that's actually the correct answer. They fake
Wait.
colored it yellow to make you feel better about the sun because we're stupid, okay? And if we see the sun in indigo light, that's going to bother us. And we're not going to feel good about it. So they, even though it was taken at purple wavelengths, they just colored it yellow because you're used to thinking of the sun as yellow. In
What's
fact,
the
from
point
outer
of doing
space, huh?
Like, why would they do that?
Because if you see a purple sun and you don't know shit, you don't know anything about the EM spectrum, okay, then you're going to be confused as to why you're looking at a purple disk.
I don't
They
know.
color
I'm
it
gonna do
yellow,
it
right? Because what color is the sun from space? What if we really showed this in true color? What color is the sun from space?
You said it's white.
Pure white. And obviously, if they show you a white picture, you'll feel like you got robbed. I've spent all this money on NASA and I didn't even get a color picture. Okay, so they can't do that either.
Wait, are you talking about because people will create like conspiracy theories? Is that why? Is that the legit reason why they do that?
Well, no. It's because you want to explain to the public what the sun looks like at visible light, and this sort of cues it says something without saying any words. Anyways, let's not get distracted by that, Vladimir. Do you guys want to see a video of what the sun does during a typical day at visible wavelengths? Here we go. Play. Now, this might be a little jerky over the internet here, but what you can see is the sun slowly rotating. It sure looks like it's slowly rotating, except you guys probably don't realize that this is a ball whose diameter is 1.5 million kilometers across. This sunspot here, this is a sunspot, by the way, we should talk about them. It's moving maybe one sunspot diameter every hour or so, right? Now, it's hard for you guys to really get a sense what a ball 1.5 kilometers in size is. So let's have a little fun here. I just want to do like a little goofy exercise with you for kicks. And I want you guys to do some dimensional analysis with me. Okay, does anyone have a pencil handy and can write down these numbers? I'm going to take my ruler here and I'm going to measure the diameter of the sun in centimeters. It's 12.5 centimeters on my screen. That's the diameter of the sun. And now I'm going to measure the size of one of those sunspots. Ooh, all right, I changed the scale of it. I think it was about 4 millimeters. Okay. All right, this is an exercise to see if you guys have learned the skills that I've taught you so far. Let's play a game called How Big is a Sunspot? Or how big is that sunspot, rather? And you guys might understand where I'm going with this. Maybe you've already worked it out. How big is that sunspot? We have a ball. What was the diameter again? 12.5 centimeters?
Yes.
And the sunspot was 4 millimeters in width, okay? Now, I can tell you that the true diameter of the sun is 1.4 million kilometers. Can you guys think of a method or a technique that I might have taught you which would allow you to figure out how big that sunspot is in reality? This is something we learned about in the first week when we had to build a scale model. Hold on, let me get some ice water. Think about that. Sorry, guys, but there's a lot of thirstiness going on in this room today. Hey, what am I going to do? How do I figure this out?
Analysis?
Yes, Mateus, dimensional analysis. Why don't you walk us through it? What should we start with here, do you think?
12.5 centimeters.
I don't think that's our best bet. And let me explain my logic. Remember, Mateus, that our job is to find out the size of the sunspot. That makes me think that we should start with the sunspot. That's what we're trying to transform into.
I think I know.
Okay. What do you think, Andy?
The 1.4 times 10 to the 6 kilometers.
No.
Is it
Once
the
again,
millimeters?
Mateus started with the 12.5. You're starting here, but my point is, it's the sunspot that we're trying to analyze. We should start with the spot.
Probably convert it into say meters. I did everything in meters, so I'm converting it to meters.
No, Vladimir, I appreciate your reaching towards MKS as an instinct, but to measure the size of a planet, kilometers are a much more tasteful unit than meters.
Oh, yeah. All right.
Right?
I mean, oh yeah, I converted. Okay, I did go back to kilometers. That's yeah.
All right. Who knows what to do? Just tell me what to do. Yes.
Yeah, convert the
Kiana.
sunspot size.
Wait, did you say nanometers? Those are millimeters. I don't know what you. Kiana, did you mean to say nanometers? I'm not sure. Kiana, you just shouted out 4 nanometers at me. I'm not sure what that means. No, you. Oh, okay. Mateus, did you follow me?
Yes. So you start with the 4 millimeters.
Yep. Then what do I do?
And then you transform it into centimeters.
Yes. So let's do that quick because I've got a lot to cover today. What's the conversion factor?
1 centimeter equals 100 millimeters. Oh, 10. Oh yeah, it's 10 because it's in the ruler. Yes.
Okay, all right. Let's not forget. Okay, all right. Then what do I do? So now I know that I have 0.4 centimeters. So what?
Right.
Now
So now you're gonna take the 12.5 centimeters.
Hold on. Let's do this dimensional analysis style. Units
Okay.
first, numbers second. That's the secret to success. You understand what I mean by that? Put some units in this bar for me.
Okay, so we're gonna turn centimeters. Let me try to explain what I was trying to do. Compare the 12.5 like in a division bar, and then do 1.4 times 10 to the 6, and then under it do 0.4 centimeters, and then do a division bar in X, and just do cross.
The problem with your method is there's a million ways to think badly and screw that up. The
Okay.
virtue of my method is it's impossible to screw up. I'm trying to train you to not think like that, to not start grabbing numbers and swashbuckling around your page like some mathematical Zorro. I'm trying to get you to have control, and units are the way that we have control. So let's analyze the problem. You know how big your sunspot is in centimeters on the screen, but you would really like to know how big the sunspot is in what unit?
Kilometers.
Right. So why don't you do the dimensional analysis to make that happen?
Okay, so you do centimeters in the bottom and kilometers on top?
Yes. And now you need a conversion factor. What is your conversion factor from centimeters to kilometers?
12.5 centimeters equals 1.4 million kilometers.
Right. This is kind of like a conversion factor. It's a scale factor. Now we're doing this clean and neat, and we can be sure that we haven't screwed it up because the units have guided us. Okay, punch them up. Do 4 divided by 10 times 1.4 million divided by 12.6.
I think it's supposed to be 12.5.
Yeah, sorry. I don't know what that was all about. It won't change the answer too much, but fine. Fine, you third sig fig quibblers, you.
Is it 112,000 kilometers?
That sounds too much. Did you read that wrong?
I think I didn't factor in the 10. 1 second.
I have 44,800.
Yeah. So let's
I
just
got that too.
let's just call it 45,000 kilometers. What does that mean? Suppose I told you that Earth has a radius of 6,400 kilometers. That means the diameter of Earth is 12,800 kilometers. What's my point?
The sunspot's really big.
Like how big? Be quantitative instead of qualitative, Mia.
Three
Really,
times
really
bigger.
big is bigger than sort of tiny small, right?
3 times bigger than the Earth.
Yeah. That sunspot, 4,500 divided by 12,800, is 3.5 times bigger than planet Earth. Look at that thing. That's 3 Earths across. And look how big this ball is. Do you understand now how stupidly, insanely huge this thing? And watch the video. This thing is rotating. I mean, I guess that means this thing's rotating. If it moves 1 sunspot per hour or so, it's kind of moving like 3 Earth diameters in an hour. That is not a slow rotation. That's a rapid rotation. But the ball that is the sun is so darned big that it doesn't look like it's moving fast because you're looking at such a gargantuan object. You know what I mean? There's another point to this story, which is when you look at the sun at visible wavelengths, the sun is boring. The sun just has a perfectly uniform illumination of pure white light coming off its surface. And the only thing that even breaks up the emission of white light is the occasional sunspot. Other than that, at visible wavelengths, the sun is a pure radiation field. I was sad to lose Philemon because, man, this is where we're going to start to get into some good stuff. What if I then image the sun at X-rays? Do you want to see the exact same video taken at the exact same time, but see what happens when you change the wavelength of observation? Now, instead of visible light, let's tiptoe ahead and see what the sun looks like at X-ray wavelengths. This is the same image of the sun taken around 10 nanometers or so, maybe 18 nanometers, or sorry, 17 nanometers. And watch this, same period of time. Suddenly you see the sun's not so boring, but if you look at other wavelengths, you see dramatic solar flares and prominences of plasma that just stick off the surface. Up here where my mouse is, we're about to see a dramatic solar flare where magnetic field lines poking out of the plasma of the sun wind up and twist up to the point where they build up magnetic tension and snap, and boom, they eject plasma right off the surface of the sun into outer space. The sun is totally insane. It is violent, it's evil, it's full of these twisting magnetic field lines. What the hell is going on here? I don't know, but it looks cool and I want to know more about it. Stars are wild. They're completely wild. And the Solar Dynamics Observatory lets us see some of that gritty detail. Okay, so we're going to do a little bit on the sun. It's going to take us a while to go through it because it'll set the tone for all the other stars that we study. And let's see, I've been pretty wasteful in class. Oh God, it's already 12:43. All right, we can do this. This will be your preparatory day to learn some basic stuff about the sun. And then we'll get into like the core and the nuclear fusion and all that. I don't think we're going to be ready for the sun homework today because there's so much for us to learn. We're going to have to go through spring break next week and do more on it before we're ready to solve some of those problems. So, okay. Let's start off with some general notes about the sun, some things that you need to know to learn about what makes that object tick. A somewhat boring but necessary place to start is just to learn some basic facts about the sun. Did you see how my exercise with the sunspot showed us that it's when you look at that ball on your screen, it's kind of hard to contemplate how big it is until you realize that one of those sunspots is 3 times the size of Earth. Here are some numbers to go along with the sun. We can talk about its fixed dimensions. These are numbers associated with the sun that never change. And in fact, I'm doing something even deeper right now. I'm basically going to list for you the 4 key parameters of any star that we're going to have to be mindful of going forward. The sun has a fixed mass. That does not change. 2 times 10 to the 30 kilograms. Interestingly enough, the sun's luminosity is relatively constant, at least over our lifetimes. The luminosity, the light output of the sun, is a fixed 4 times 10 to the 26 watts. You've seen both of these numbers before, but we should write them down again. I should point out in the spirit of honesty that stars do slowly brighten over time due to changes in their nuclear reactions. They call this solar brightening, but the slope of the curve is so shallow that even over a span of a couple of million years, maybe 10 million years, it doesn't change much. It's still approximately 4 times 10 to the 26 watts.
But don't stars also lose weight? I mean mass.
That's actually going to be one of the calculations we do for homework, Vladimir. They are losing mass because they convert it into light. But I guess 2 weeks from now, 2 Thursdays from now, when we do the sun homework problems, what you'll find in the analysis, and we'll see if you can remember this then, the amount of matter the sun will lose in its entire lifetime is equivalent. Well, it's equivalent to the planet Jupiter. The planet Jupiter might be significant to you, but the planet Jupiter, yeah, the Jupiter has a mass of 10 to the 27 kilograms. So how many orders of magnitude is that apart from the sun?
Thousandth.
Exactly. So the sun, even over its entire 10 billion year lifespan, is only going to lose 1,000th of its mass. $1 out of $1,000 isn't something any of us would quibble about. So I would say it's not really losing a significant amount. But I'm glad that you know about that and brought it up. 2 other properties of the sun that stay fixed, and this is kind of interesting. The radius of the sun remains fixed. 700,000 kilometers. Now, nobody thinks it's weird that the radius of Earth stays fixed, but that's because the Earth is a ball of solid rock and metal. And as you know from personal experience, rocks tend to keep their dimensions unless they are like greatly manipulated. The sun is not a ball of rock and metal. The sun is a ball of gas. Here's a thought question. Why should a gas ball in space keep a fixed radius? Gases just tend to fill up a room and do whatever the hell they want to do. They are volatile by nature, right? The sun's radius stays perfectly fixed. I'm going to talk about that later. The last property of a star is its surface temperature. And let's write underneath surface, because today you're going to discover that there are many, many different temperatures associated with the sun. But the surface temperature, okay, Nick, no problem, buddy. Just catch these lectures later, okay? As some people discovered, not watching the lectures has painful consequences later on. So, Nick, do your thing, but catch this later. The surface temperature of the sun that visible layer that we could see with the sunspot remains fixed at 5,800 Kelvin. And I'm setting the tone for stuff that's going to happen with us later. As we go on and study other stars, you will discover that M, L, R, T are the 4 key parameters of a star. If you can measure these 4 numbers, you can analyze the physics of any star and know how long it's going to live and all kinds of other cool things. So we're going to be building a Lego house here where you learn all these kind of stars are interesting enough, I suppose, but all these building blocks are going to lead to some really cool questions if you bear with me here. Another thing that you should know about the sun, besides its fixed dimensions, is its composition by mass. And I have to mention by mass because the majority of the sun is made up of hydrogen and helium. And here are the percentages. Hydrogen gas makes up approximately 70% of the sun. So it's mostly hydrogen. The second most abundant element in the sun is helium. Helium, of course, was only discovered by analyzing the spectrum of the sun. And the element helium is named after Helios. 28% helium. And the remaining 2% gets a funny name in astrophysics. The remaining 2% are what astronomers call metals. But metals is it's a charged term in astronomy. Metals really means for astronomers any kind of heavy element that you can imagine, including carbon, nitrogen, oxygen, neon, iron. Oh my God, it's all in there. Titanium oxide, every kind of damned element you can imagine shows up in the sun sooner or later because the sun's just insanely massive. This is a little kids break that we're going to do for a moment to explain metals versus metal. Okay, now, if you ever took a chemistry class, let's look at a cartoon picture. Do I have a cartoon picture of the periodic table? That would be like helpful. Why can't I? Sorry. Do we have a periodic table of the elements? No, but I do have one in my previous slideshow here and here. Okay. How many of you have taken chemistry before? Okay, a few of you. So just in case you remember stuff from your chemistry class, which could be dangerous. Okay, Tegan has too. When I took chemistry way back in the day, I learned that there were 2 types of general elements in the periodic table. There were metals, and everything kind of on the middle to left side of the periodic table. Those were metals. And then I learned that there were non-metals or insulators or things like this. And chemists go through a great deal of trouble to explain that metals are metallic-like because they have an extra valence electron to share. And these are non-metal because they're missing a valence electron. Maybe this is ringing a bell, right? And so you can see there are different types of metals. There are basic metals and transition metals and alkali metals. And then the other things, the insulators, are noble gases or halogens or whatever. This is not how an astronomer sees the universe. Astronomers are not like chemists who have a whole cornucopia of little vials full of isolated elements that were produced by someone. Astronomers tend to think of the universe in the same way that they think of the sun. They think like this. Most of the universe, 98% of it, is hydrogen and helium. So these things are hydrogen and helium. And all this other crap, right? All this other stuff is the little bit of grit in the eye of the sun. So they just call all of this stuff metals, okay? That's how an astronomer thinks. But that could be confusing because if you say, 2% of the sun is made of metals, your chemistry teacher is going to say, wait a minute, neon's not a metal, carbon's not a metal. I know that, but astronomers don't care what chemists think. They have their own logic, okay? So keep in mind that, in fact, let's do a little exercise similar to the sunspot exercise we did. We saw that when we analyzed the sunspot, not only did we realize, whoa, sunspots are huge, But the next thought you have is the sun is really huge, right? Let's ask ourselves, what is the mass of the 2% metals in the sun? Okay, so let's keep these numbers up for reference. Does everyone have this? Andy, do you need a sec here?
I got it.
All right. Let's do a really lame little exercise that's kind of similar to something we're going to do in the homework. What is the mass of the 2% metals in the sun? And furthermore, how would it compare to Earth? This should be wicked easy, right? What do you do? You guys know what to do, right? Sorry?
You multiply 2 times 10 to the 30th by 0.02.
That's right. So when we convert 2% into a percentage, it's 0.02. Hey, Vladimir, I got a fun exercise for you. Let's do this in our heads, okay? So let's multiply our lead digits.
So it's 4, then you take 2 from the 30.
So my final answer?
4 times 10 to the 28th.
28 kilograms. Nice. Now let's remind ourselves that the mass of Earth is 6 times 10 to the 24 kilograms. Should we keep going and see if we can do it again? What's 4 divided by 6?
2/3, like
60.
0.67. Yeah.
All right, so 0.67 times 10 to what power?
4th.
Fourth. But now let's do this. Let's slide our decimal place over there. What happens to our power?
The classic style.
Yeah.
So it's 6.7 times 10 to the 3rd. Oh,
Which is what?
6,700. Oh wait, no, it's more. It's
No, you did it right. 67.
Oh really? Oh.
You're right, yeah. That's 6.7 times 10 to the 3 means you've got to move 6, and then you move your decimal place 1, 2, 3, right?
Yeah.
Okay, so what's the point of this problem that we? Cool. Do you see how Vladimir just did that in his head? Anyone can do that if you know what 2/3 are. Okay. Anyways, what's the point? What does the 6,700 mean now?
It means that we could really use those metals.
Right. It means this is 6,700 Earths worth of metal, right? If you could just squeeze.
2%.
Say that, Vladimir?
So just puny 2%.
Right. And this isn't even the hydrogen, right? Like, if you could just squeeze that little grit out of the eye of the sun, you could make another 6,700 terrestrial planets. I mean, after all, when you start to think about the solar system as a thing, and here let's just call up a picture of the solar system. I like the one on Wikipedia. I like this picture here. If you think about the solar system, the planets are kind of like the condensed 2% metals that were rotating a little too fast to fall into the sun. And the mass of these collective planets is even thousands of times less than the total metal content of the sun. So these are what happens when you crustify these little tiny bits of metal in outer space that didn't quite make it to the sun. Of course, it's going to turn out, if you take my solar system class like Philemon is, the composition of the gas giants is basically identical to that of the sun. They have the exact same percentages that I just taught you. So these are kind of like mini failed stars. But somewhere down in their core, they have a terrestrial planet with ice buried in there. More about that if you take my 1010 class. We want to talk about stars. Okay, so I'm going to erase this. That was a cute little exercise on percentages and helping you think about just how massive and how big the sun is. So let's get on to, wait, am I going to forget anything? Oh, we should probably talk about gases in plasma. Do you guys remember what plasma is? We've had a very brief conversation about it. I ain't talking that blood.
Charged gas.
It's a charged gas, right? So here's the idea about the sun, something to consider. the sun is a mixture of neutral gas and plasma. And these two things are somewhat related to each other. That's because the sun has a number of different temperatures associated with it. Let's remember the difference by drawing some cartoon pictures. Knowing that we do now that the sun is mostly hydrogen, here's what neutral gas looks like when you consider hydrogen. It means you have some protons, and it means the electrons are bound to the atoms themselves. And this, well, I shouldn't get those too close. You're going to get the wrong idea. But the idea is that in a neutral gas, the electrons are firmly bound to the atoms and orbit them. And that means if you zoom out from the gas particles, they are electrically neutral because there's one negative charge for every positive charge. In other words, neutral gases basically behave like little ping pong balls. If you squint your eyes and you don't look too closely at the fact that there's an electron and a proton, they are basically the same as ping pong balls, just on a smaller scale. They bounce around and they bop into each other, but they don't have any charges between them or anything like that. The situation changes when you raise the temperature such that the electrons start to hop off of the atoms. Then you still have hydrogen, but now your hydrogen is in ionized form. And that means you kind of have a mosh pit of free protons, okay, and free electrons. And the electrons are all zipping around nearby, but they are no longer bound to the protons because their kinetic energies are so high. And plasmas behave somewhat differently than a normal neutral gas. And that's because just like when I play with these magnets here, I wish I meant to buy a set of these. I think I even did for my office, but I forgot to steal them. You know, marble magnets? Marble magnets are kind of fun to play with. And if you've ever rolled marble magnets around on a table, the magnetic forces between them cause them to deviate and deflect and bend their paths, right? I really should get a set of those so we could make a fun experiment out of it. Plasma particles are not going to bop around in a straight line like a normal neutral gas. They're going to have electrical forces, electric fields that connect the protons and the electrons, and they're going to generate magnetic fields as well, because when charges move in a straight line, that generates magnetic fields. So in addition to the normal mosh pit of these things moving around like ping pongs and colliding into each other, there's also going to be deflective magnetic and electrical forces. Plasmas are actually quite complicated to model because of this. For instance, if I were to not consider plasma, if I were just to consider neutral gases, where's those PowerPoint shows again? Unfortunately, my darned flash files aren't working right now, and I can't figure out how to get around that. But this is how gases behave when they are neutral. Let's pretend these are the gas particles in the sun. The blue pellets might represent the 70% hydrogen, and the red pellets represent 28% helium. Even though helium is more massive, they basically just kind of act like little ping pong balls, and they sort of collide with each other. Now, I searched in vain to try to find a similar animation except for plasma, and I could not do it. I could not find a good, simple animation for plasma. And I started to realize the reason why is mathematically calculating those trajectories is way more complicated for a plasma than it is for a natural gas. In fact, here's something kind of interesting. This is totally over your pay grade. I'm just trying to see if I can find this legendary book that I had to study from. Chen's plasma physics is up here. And without going off of the total deep end, I took a graduate course. The entire course was plasma physics. And that course hurt my mind. Okay, it was so mathematically complex. Oh, late nights and differential equations, stale coffee and styrofoam cups. You don't want to hear about it, okay? I suffered the tortures of the damned. But here's one thing I do remember from plasma physics that's a cool takeaway. What ends up happening when you have free electrons and free protons and you jack up the temperature is kind of similar to what used to happen in those junior high school dances when none of the boys and the girls could like talk to each other because they were too shy. Well, it's kind of interesting. All the protons are kind of trying to stay away from each other, but they end up kind of locked in place. And all the electrons are trying to stay away from each other, but they kind of end up locked in place. And then all of a sudden, all of the electrons try to go and collide with the protons, but they're moving too fast. So they kind of zip by them and the gases end up oscillating back and forth. And plasmas actually oscillate and ring like a vibrating bell. And they actually develop plasma waves from their oscillations. And believe it or not, in some of the solar dynamic videos, solar dynamic observatory videos, you can actually see those oscillating plasma waves moving across the sun. Let me share this with you because it's just so beautiful. I want to really encourage you guys sometime to go to YouTube, and there's a really cool summary of like the Solar Dynamics Observatory's greatest hits, and it's called Thermonuclear Art. So you type YouTube thermonuclear art, and what's pretty cool is it's in 4K. Now, it also has some creepy space music too, which I like. I actually splurged a few months ago. I totally could not afford it, but because I'm an AV geek down to the dyed-in-the-wool like audio-visual geek, I splurged for a 4K projector. It was an indulgent purchase that hurt my bank account badly. But can I tell you, oh my God, is it so awesome. I put this video on my 4K projector and project it all giant on the screen. And I'll just sit there and just like, you know, drink tea and look at this thing. And it is like, it's like you're meditating on this like evil ancient god or something. But speaking of plasma waves, so anyways, if you have a cool, like modern computer screens usually will show 4K, you can literally get lost in the details. I'm broadcasting over the internet at supposedly 720p, but I think it gets crunched down. But let's hit play on this. Let's mute the music, although it's kind of cool. This is probably grainy, but can you guys see these like little wave fronts? When you watch it yourself, you'll actually see these walls of plasma. You can actually watch it like a water wave just rippling across the surface of the sun. And watching the chaos of plasma, honestly, this video wasn't available to me when I was a grad student in plasma physics. And I think if it had been, I would have been more excited to do my differential equations because I didn't get to actually see this. I had to like look at the math and think about it. And that's not quite as riveting. Okay, so the fact that you guys are studying at a time where you can see videos like this is so inspiring that it would have meant so much to me if I could have seen that. Okay, we'll talk about the sun being a mix of plasma and gas, but let me give you the sort of big picture now, because today's class is about big picture things of the sun. If you had to ask me what fraction of the gas, what fraction of the sun is gas and what fraction is plasma, I would say the answer depends upon what part of the sun you're in. So here's a picture of the sun. And this outer layer is the surface, or this is what we call the photosphere. And the photosphere, as you know, the surface layer, I told you has a temperature of 5,800 Kelvin. Now, 5,800 Kelvin is hot, okay? That's certainly warmer than your oven is when you're cooking Thanksgiving dinner. But there are much higher temperatures in the sun. So at the surface, the sun is warm, but it actually gets hot in both directions. The sun gets hotter as you go towards its atmosphere. And then if you burrow in towards the center of the sun, it's insanely hot. So this is a lame ass cartoon to show you the temperatures are high everywhere, but weirdly, the photosphere is the coolest layer of the sun at 5,800 Kelvin. So at the photosphere, you have probably something like, these numbers are not exact. I'm kind of exaggerating, but this is the vague memory I have. It's maybe 95% gas and 5% plasma. And in fact, I think those numbers are too high. I think at 5800 Kelvin, like 2 to 1% of the gas is in plasma. I'm kind of lying to you because I feel like that'll be better for you to think that there's more plasma there than there is. But it's the surface of the sun is mostly gas. Okay. In fact, if I had to be really honest, it's probably 98% gas and 2% plasma. However, at the outer layers of the sun, called the corona, it's probably 99% plasma. And by the way, when you get into the interior of the sun, it's 100% plasma. Now, in a sense, as Vladimir said to us, plasma is also a gas, right? It's a charged gas. But this means that I'm going to say things that might sound confusing. Sometimes I will say the sun is a ball of gas, and that is true. Sometimes I will say the sun is a ball of plasma, and that's also true because most of the inside is plasma, the outer wispy layers are plasma, and the only bits of neutral gas are towards the surface. The truth is complicated. The sun is a mixture of gas and plasma, okay? I want us to think about that beforehand. Plasma usually involves the creation of intense magnetic fields. And we're going to talk a little bit about those at a later time. You guys probably don't even know what a magnetic field is. We'll try to give you a little more insight into that as we go. Do I have time to do hydrostatic equilibrium? I do. Okay, cool. So 2 things before we get going. We have to review a classic law about gases, and then I want to talk to you guys about why the sun keeps a fixed radius. Have you got this? I'm erasing. Okay, we have to review some basic ideas if you're going to think about a big ball of gas. Let's talk about something called the ideal gas law. This is a law that governs the motions of gas particles, definitely when they're neutral, and you can actually use this sometimes for plasmas too, provided they're not too densely packed. If you ever took chemistry, and a couple of you did raise your hand, you probably learned a goofy version of the ideal gas law. And I believe the kids call it PIVNRT, PV equals NRT. This formula is for weak sauce chemists who can't handle the truth, okay? Actually, this is the truth, but they like to think of gases in terms of volumes and numbers of particles. Chemists are always trying to count the number of moles and atoms and things because they deal with these little samples that are this big. This is a totally inappropriate version of the ideal gas law if you want to think about something as massive as the sun. The physics version, the real version of the ideal gas law, is much more elegant. P equals NKT. Absolutely. Where P is the pressure of the gas. And I'm going to leave the units out for a second because I want to talk about pressure. N is something called the number density of the gas. And the number density basically means it's the number of particles per cubic meter of the gas. Oftentimes astronomers work in centimeters rather than in cubic meters, but cubic meters are the MKS version. So you're going to see me sometimes in this class do particles per cubic meter, or sometimes I'm going to do particles per cubic centimeter. And that's going to actually be more common. Now, I'm trying to give you guys a sense of what a cubic centimeter is like. Can you think of something from your everyday life that's the size of a cubic centimeter? I have the perfect little doodah, maybe over here in my game section.
Yeah, I have a cap from a bottle, from a really small bottle. Does that work approximately?
I was even thinking like a dice, right? Wait, let's see. I think a dice might be a little bigger. Oh, wow. So a dice is like just over, it's close. I actually had a mini dice and I kept it around here, but I think someone came over my house in some drunken bender and probably took it or threw it or something. But look, you can see this standard commercial dice is just a little bit over a centimeter on an edge. So, you know what, Marshall? Getting robbed of my tiny dice hurt my feelings because I loved those little tiny dice and they're here, I hope somewhere, or someone knocked them over or threw them, but believe it or not, these are the things that keep me up at night. Anyways, this dice is a little bit over a cubic centimeter. You know, like a chicken bouillon cube or a sugar cube, that's about a cubic centimeter. Now, what a cubic centimeter, what a number, oh, let's get back to my focus here. Let's focus on cubic centimeters. Okay. The number density basically means if you have a little sugar cube worth of space, you're basically asking how many atoms are bouncing around in that box. So for instance, if you had 5 particles of gas inside of a box the size of a dice, you would have 5 particles per cubic centimeter. But particles is not a real physical unit. It's what you might call a dummy unit or a conceptual unit. The actual units of number density are kind of disturbing. It's 1 over cubic centimeters. People don't like to see things in the denominator of fractions. That tends to bother them. So when I say per cubic centimeter, if you feel disturbed, feel free to put the particles back in your mind and think of it as atoms per cubic centimeter or particles per cubic centimeter. However, I should warn you that sometimes astronomers write this, and when they're feeling especially mean to their students because they know that they're better than them at math, they'll even sometimes write it like this: 5 centimeters to the -3. Because if you put the centimeters in the top, you change the size. So this is actually how professional astronomers write particles per cubic centimeter. They write 5 centimeters to the -3. And that just downright scares folks, okay? But when you see this, I want you to know in the future that that just means number of atoms in a sugar cube, okay? That's all there is. Particles per cubic centimeter. The number density tells you the number of particles in your box. The pressure we're going to get to. K is a constant of nature that deals with gases. It's known as the Boltzmann constant.
Again?
Okay, so I was wondering if you
That
picked up on that, Vladimir.
Stefan Boltzmann. That's just Boltzmann.
Exactly.
Is it a different person?
No, see, this is why we're confused. It's because Boltzmann was such a badass. He did all these different things, and now he has 2 different constants named after him. Sorry, Boltzmann, you had to be an overachiever, and now we're confused in our science class. Boltzmann is known for the Stefan Boltzmann constant. The Boltzmann constant is all his, and this number just comes up anytime gases are being analyzed. There is physics behind it, but at your level, you're not allowed to know about that. It's 1.6 times 10 to the -23. The units are a little bit weird. Joules per Kelvin. Did I get that right? I'm having a forgetful day. Let me just type the. Actually, I want to keep this thermonuclear art up. We might like that. The Boltzmann constant. Oh, sorry. It's 1.4 times 10 to the -23. I don't know where my brain is today. I knew something was wrong there. 1.4 times 10 to the -23. Don't worry about the Boltzmann constant for now. T stands for temperature. And what units do we measure temperature in?
Kelvins.
That's right. So these will be measured in units of Kelvin. All right. You'll notice that I gave you the units of number density. I gave you the units of the Boltzmann constant, the units of temperature. I've not given you the units of pressure yet because I think we need to have a discussion about pressure. What did we say the definition of temperature was? from one of our earlier classes.
Average kinetic energy of all particles in a gas.
That's right. So the true definition is it's the average kinetic energy of the particles. You'll also remember, Vladimir, that I told you guys what I consider to be a use, that looks like particles, but it's particles. Let's just say atoms, okay? Average kinetic energy of the atoms. A useful way to think about temperature, which is not strictly true, is it's kind of like the speed of the atoms, right? Sort of. Higher temperature usually means the atoms are traveling at a faster velocity. Okay. Now that you remember the definition of temperature, let's talk about pressure, okay? Let me sip water while you guys finish this, and then we're going to erase. Can I wipe it? The reason we're doing this is you really need to have a good warm feeling about properties of gases to talk about a big ball of gas, right? That makes sense. Let's talk about pressure in a physics. Does anyone know what pressure is? Vladimir, you seem to have some science background, maybe. Do you remember how we define pressure?
Can I just make a shot in the dark? So I would say it's some amount of force per some amount of area.
That's
No?
exactly right. That is the definition, straight up. It's force per unit area. And what we want to do is we want to have a picture of this. Let's imagine, oh, fun demo time. Just so happens I've got a big old vat of balloons in my house, strictly for non-scientific purposes. And here we go. We have a rubber membrane, that's the wall, and we've filled this thing up with gas. We've pressurized it, okay? And let's imagine we could analyze a little fragment of that rubber membrane, okay? So here's the wall of my balloon, and there's some gas particles in it, okay? So maybe I'll even try to make this 3D and, you know, sort of extend myself here today, okay? So here's your unit of area. There's the wall of your balloon. And here comes some atoms, some gas particles, which are crashing into the wall of your balloon, and they're imparting some force per unit area. This might, okay, so I don't really think I have a square meter here, but I could easily get a square centimeter by drawing a little square about that big, okay? So it's, if I wanted to do it as force per unit square centimeter, I could do that. And it's the number of, what are the units of force again in the MKS system?
Newtons per square meter.
That's right. So the units in the MKS system are newtons per meter squared. And we define a Newton per square meter as a Pascal of force. The abbreviation of Pascal is PA. As a reference number to consider, the pressure of air at sea level, which is pretty close to, think about it, Rhode Island is at sea level. So this is the pressure roughly of the air in the room that we're all breathing. The pressure is 100 kilopascals, which of course is 100,000 pascals. And that's the pressure of the air that's surrounding your face and your eardrums right now. In fact, let's do a couple of comparisons of different units of pressure. This would be really good if any of you have taken my, or are planning on taking my solar system course. Andy, are you done taking these notes here? I'm trying to tell if you guys are writing. Mateus, are you done?
I'm done.
All right, I'm gonna erase. Just a quick comparison, because it's also cool when astronomy can like teach you some basic stuff about life. If we wanted to do units of pressure and just do a quick comparison. MKS, you just learned about the Pascal, which is 1 Newton per square meter. Do you guys know what they use in imperial units? If you've ever gone to fill up the gas in your tires, fill the air in your tires, what do you use?
Pounds per square inch squared.
Yeah, well, no, it's PSI
Yes.
is just pounds per square inch. You can see it's still a unit of force divided by a unit of area. And air at sea level is 100 kilopascals. So those are our metric MKS units. But as any auto mechanic or diver knows, in imperial units, I believe it's 14.7 pounds per square inch, right? Sometimes it's cool to just look at like, you can actually do this next time you want to check the pressure in your tires. If you look at a tire pressure label, usually your tires will tell you at the edge of your tire. I want to see it actually on the tire itself. What do I type? I wish, do any grease monkeys in the house here and know tire? What am I doing wrong here? Like on a car tire, you can actually see the pressure labels, right? I ain't crazy. Here we go. No. Oh, I always have trouble. There's one picture that's pretty nice. They'll tell you usually somewhere on your tire. Oh, here we go. Max pressure is 35 psi. The cool ones give you the metric units too. So 35 psi, how many times greater than atmosphere is that? What's 35 over 14.7?
Kind of like maybe 2.3.
Yeah. So your tire's only inflated to 2 to 3 times air pressure. Do you know how much PSI you usually put in a bike tire? I pump up bike tires all the time because I love riding my bike around the city.
I'm gonna say 5. Just
Yeah.
because.
Yeah. So if your car tires are at 35 or 40 PSI, I often pump my bike tires to 80 PSI. One of the weird things about inflating tires is bicycle tires are at many more times pressure than car tires. And that seems counterintuitive. You'd think a car weighs so much more than a bicycle, you need more pressure. But because it's force per unit area, the surface area of tires is so much smaller than the surface area of car tires that you actually require a higher pressure to keep a bike aloft than you do for a car. Isn't that wild and sort of counterintuitive? I never would have predicted that. I would have thought it was the opposite. People who work in planetary science often use atmospheres. 1 atmosphere of pressure, and these are good for measuring planetary atmospheres, is really close to 100 kilopascals. There's some kind of slight difference in the average. I don't remember the reason why. People who work in meteorology work in bars, and I believe 1 bar of pressure is 100 kilopascals. So bars and atmospheres are the same, but depending on who you're talking to, people will use wildly different units. A physicist would use pascals. A car mechanic uses PSIs. Planetary scientists who study Mars will use atmospheres. Meteorologists use bars. I just wanted you to hear about this first, okay? Now, in the sun, there is a balance of pressure and gravity. And this will be my last note for you guys for today. I kind of went a little nuts on pressure there. Sorry about that. But, you know, stuff you should know for life. The last thing that I want to cover today, and I'll leave it here, is if you look at a cool picture of the sun, like, for instance, here. This picture is interesting to me. I just grabbed this years ago off the internet, and I thought it was cute, okay? What this picture reminds me of, several different things, is although the sun's quite bright, you can see the sun with your naked eye. Of course, it's really not safe to look at it with the naked eye. It's better to have some of those solar eclipse glasses. But when the sun is through a thick smog of clouds or something, you can see the disk of the sun with your naked eye. And you'll remember its angular size is half a degree, or roughly half the width of your fingernail at arm's length. If the sun's radius changed, you would actually see it. And later on, when you guys learn about other types of stars, there is a class of stars called variable stars. And those stars actually pulsate and their radii oscillate. Could you imagine if we were born on a planet surrounding the star Polaris? Our sun would grow and shrink in the sky over a course of a month. And that would be like a weird and wild experience. In fact, I'm not sure how life could adapt to that, because when stars' radii grow or shrink, they pump out a lot more light. And of course, the Earth is already warm enough as it is with our sun at a fixed radius. All of these things get me thinking, how can the sun maintain such a perfectly fixed radius when it's a ball of gas? After all, if you open a bottle of perfume in a room, the molecules spread out. If you ever watched a science fiction movie, like I'm a sci-fi geek to the max, what happens when they open the pod doors there at the airlock? All the gas goes whoosh, and it whooshes out into space, right? Why don't the gas particles of the sun just disperse?
I mean, the same question, why doesn't the atmosphere of Earth doesn't just disperse into space, and why don't we just all die?
That's true. And do you know the answer to that question? They're kind of the same answer.
Gravity?
That's right. The sun is held in place by gravity. Now, on Earth, it's easy to imagine because we're used to sticking to the Earth, and you think of the Earth as a solid rock, but the sun is not solid at any layer. It's just a big ball of gas. And the answer to that question is a buzz concept in astronomy. It's called hydrostatic equilibrium. And what hydrostatic equilibrium is, it's an answer to the question, why does the sun maintain a fixed radius? Why does it keep its shape? Okay, so hydrostatic equilibrium is this. It is a balance of forces between gravity pulling in and what we would call thermal pressure. And thermal pressure is just a way of saying the kind of pressure we associate with the ideal gas law. So I'm going to write the ideal gas law underneath it. T equals NKT. It's a balance of forces between gravity pulling in and thermal pressure of the gas pushing out. So sometimes I draw the picture, but I'm kind of out of time here. Let's share my slideshow instead. And somewhere around here, yeah. So gravity pulls the star in, gas pressure pushes out, and the two kind of come into a perfectly stabilized balance, all right? In a way, this also reminds us that stars generate their internal temperature at first from just gravity squeezing the star. Gravity squeezes the ball of gas and the gas gets hot. Now, this doesn't tell you the whole story. Eventually, we need to learn that there is a nuclear fusion bomb going off in the center of the star, and that's going to continue to support hydrostatic equilibrium. But for the most part, not only is the sun in a form of hydrostatic equilibrium, but a planet like Jupiter or Saturn, they also maintain their radius through hydrostatic equilibrium. At first, when you learn this, it seems kind of stupid. It kind of seems like, oh, no, duh, this is dumb. But it actually turns out to be more sophisticated than you might think. And having this thought in your head is going to prove useful to us. Okay, I think that's all the time I've got for today. Let's do a reminder here. Our proposed plan, because I do not believe we are ready to tackle the sun homework, is we're going to do our lenses and telescopes lab today, which will be kind of cute and fun. Next week is spring break, right? Woo, Cancun. All right. Not okay. Anyways, I guess
I didn't even know it's coming.
Yeah, I forgot about it too. I actually think I might go somewhere this spring break. I might actually go to New York to visit a friend, but just for a couple of days. I'm thinking about going somewhere. I don't even know. There's not much to do anywhere these days because of COVID, but maybe it'd be nice to like just be out of my apartment for a little bit. Anyways, I hope you guys have a chill, relaxing, and safe spring break. We won't meet for another week, but when we do get together the week after spring break, we'll do more sun stuff. And the week after, we're going to do a sunspots lab, and then we'll do the sun homework. So that'll kind of match up nicely. This is the perfect day for us to do lenses and telescopes, and it'll actually take less time than doing the sun homework. So we'll kind of get out a little early today. That sounds like fun. Let's do our typical, while you're waiting during the tea break, those of you who like to print stuff out, it's just one page that we're going to need today. Sorry. Let's get rid of this. And Andrew's already done this, so he's good. Like you don't need to, Andrew, you could actually watch the video from last class. There's 2 pages, but I think we'll probably just use the first page. If you do not have a printer, I need you to kind of take a ruler and make this. You do not need this section. We're just going to need the first, second, and fourth section. And you know what? If you have a printer, print out the second page just in case. There's a cute little exercise here that we might want to do if we move fast enough. I almost never move fast enough, but I might want to just do one of these if there's time. We'll see. Okay. Let's see. iPhone time is 1:40. At 1:55, lenses and telescopes. Sound like a plan? All right, I'll see you guys then. Okay, Astronomy 1020. Welcome to our special lab. Once again, we normally do homeworks on Thursday, but I decided a funner way to spend our last day before spring break would be to do an extra lab rather than the homework that we're not ready for yet. Just a reminder to everyone who doesn't know what's going on. Today's lab is lab number 7, lenses and telescopes. So we're departing a little bit from the videos from last semester. Last semester, I did not do this lab, but this was the lab we did last week. Last minute, I made a decision, and it turned out to be the right decision to do the inverse square law. That was related to our lecture, and it kind of bought us some time so that we can do this lab today. We're not quite ready for our next next homework on the sun. So this is perfect. So if you're someone like Andy who already accidentally did this, okay, fine, you're set. But I actually did you guys a solid, and I left this lab open a little bit longer because I was worried that some of you might have been confused. So if you were confused, if you have not done lab 6 inverse square law, please go back and watch last Tuesday's lecture. Anyways, today we do lab 7. Please make sure you're submitting these to the proper places. In today's lab, we're going to build a very simple telescope design, the most basic type, known as a Keplerian refractor, or a refracting telescope. Now, for those of you who don't know too much about this, it would be really awesome for me to spend some time teaching you guys about telescopes, but I've got so much other cool stuff to tell you that I can't afford a whole chapter on it. So this is basically, this is it. This is what I have time to tell you. Anytime you see a telescope like this with a long skinny tube, this is known as a refracting telescope. And refracting telescopes always use a lens, a primary lens, as the light gathering device. So if you see a Galileo style, like long skinny tube, that's probably a refractor. One of the other main types of telescopes that astronomers use, and I've got a demo over here. If instead you guys see a short squat telescope like this, this is called a reflector, because reflectors, instead of having a primary lens, they use a primary mirror. Most of the better telescopes, and certainly the less expensive, well, it's kind of complicated. The more money you pay for a telescope, the better it is. But it's easier to make a telescope with a mirror than it is with a lens. And mirrors have certain advantages that I might not have time to explain. But I basically just wanted to tell you that there are two main classes of telescopes: reflectors that use a primary mirror, and refractors that use a primary objective lens. They both work on the same optics principles, and you're going to learn a little bit about them. If you learn how to build a refractor, you also know a little bit about reflectors. But this is just so that you can ask, if you ever go to, let's say, LAD Observatory, they have a gorgeous old refractor that's really nice to look at planets through. Saturn looks absolutely wonderful through it. So you can tell them sometime if you visit them, oh, I know about refracting telescopes. Okay, the work we have to do today is so quick and so simple that this is an opportunity for us to kind of just relax and learn the basics of telescopes. That way, the quick work that we have to do, the 10 minutes of data collection, will be more meaningful, okay? So today we're going to be working with lenses, okay? This is a convex lens. It has a belly in the middle, okay? That's a convex lens. And it's just like a magnifying glass, like Sherlock Holmes might use to investigate a clue, okay? Refracting telescopes, or Keplerian refractors, use two convex lenses. So that's what we're going to be working with today. Now, I should tell you that there are other types of lenses, like the type you use for your eyeglasses. Those are concave lenses. And a concave lens, instead of bulging in the middle, it squishes in the middle, okay? And these are the two main types of lenses, convex and concave. You can actually build a telescope with either type. But we're just going to focus on the most simple type, just two convex lenses. And I'll show you how these things work. If you're curious about the word refractor, this is a word from physics. Let's go to our light slideshow here. And I want to show you a quick picture of the law of refraction so you get a sense of it, okay? So I'm going to build a couple of building blocks here, so try to bear with me because this might get a wee bit confusing. This is slide 36. Okay. The law of refraction demonstrated here happens when light goes from one medium, such as air, into a thicker medium, such as glass. And you'll notice that when light travels from air, so this is a white light source, like a candle, and that is a small slit that collimates the light into a pencil-thin beam. When this pencil-thin beam of white light strikes the glass, it slows down as it enters the medium of the glass. And for reasons that it's hard to explain right now, the slowing down of light causes it to bend or to refract. And you'll notice that when light hits the glass, it refracts kind of downwards. And then when it exits the glass, you'll actually see it refract back in the other direction. This is one of the bedrock principles of optics. It's known as the law of refraction. And if you ever take a physics class and get to the third level, you'll probably end up studying this in detail. When I learned about the law of refraction, and by the way, guys, I loved studying optics. I just thought optics was the coolest, one of the coolest classes I took. This is a picture that you often see when you're first introduced to the law of refraction. They show you a cartoon of a light ray entering glass, and it bends towards the normal. And you've probably seen this in your daily life before. Like if you've ever seen a stick in water and notice that the stick appears to be broken, that's basically an exercise in the law of refraction. The stick is, of course, not broken, but when the light bouncing off the stick goes from the surface of the water into air, it also bends and refracts, and it makes the stick artificially appear broken. Why, hell, there's all kinds of cool things you can do with the law of refraction. But one useful thing that you could do is, if you were a clever person, you could go ahead and take a piece of glass and shape it in just the right way. And it turns out the shape turns out to be a parabola. If you cut glass in the shape of a parabola, something very interesting happens. Light rays which strike the glass are all going to bend by slightly different amounts depending what angle they hit the glass at. But all of these light rays will bend by slightly different amounts, and all of the rays of light will then converge at a single point, which is known as the focus point of the lens. And the focus point is the point of a lens. In fact, if you were a little pyromaniac like me, you know exactly where that focus point is, right? Because you can take sunlight and concentrate it into a little dot, and then you can set the woods on fire in back of your house, okay? That's what I did. So you guys know all about this focus point. Now, today we're going to be focused on the focus point. Our goal is to measure what is known as the focal length of the lens. And I'll explain why in a second, but the focal length is the distance from the lens to that focus point where you concentrate sunlight, okay? The whole purpose of a lens is to bring light to this point. So we name lenses by their focal lengths. This, for instance, might be a 50-millimeter lens, telling us that the focus point is 50 millimeters away. This could be a 20-millimeter or 30-millimeter lens. Your goal today is to measure two focal lengths. The reason why we're going to be measuring the focal lengths of two different lenses is because they can be used to build a telescope if you know their focal lengths. So first, let's just understand that almost every optical system in nature uses a lens of some type. For instance, eyeglasses, cameras use an objective lens, and hell, even your bloody eyeball, it uses a lens too. Let's cut open your eye. Ah! And if you do that, you discover that there's this gooey thing in there that actually functions just like a lens. It's called the lens, and its job is to bring light from outside to a focus point on the back wall of your eye known as the retina. And so the focal length of the lens of your eyeball is basically the length of your eyeball. When the lens gets out of focus, of course, Mateus and Mariah, that's when we need our eyeglasses and our spectacles to correct for those changes in curvature, right? Basic detectors like eyeballs and cameras, they just need one lens, but a telescope requires two. And I want to explain why with a simple diagram. Oh, by the way, here's a point that I don't want to forget to make. One of the things you'll notice about lenses is that every lens inverts the image that it makes. And that's got some interesting philosophical implications. Everything you've ever looked at in your field of view, you've seen as upside down. But the cool thing is you never thought about it as upside down because it's always looked right side up to you. That's weird. Think about it. Your brain just gets used to being upside down until upside down is upside up. Okay, like it's just a matter of perspective. Oh, you got your peepers on there, Vladimir, too. I like them glasses. All right. So I've got some too, but I only use them for far distances when I'm focusing telescopes.
No, it's for the blue light coming from the computer.
Oh,
It's just I feel my eyes getting tight. What is it?
Are those blue blockers? Is that what they call them?
Yeah. Blue light filters.
Does it help? I've never tried it before.
I felt my eyes getting strained and dry, so I put them on.
Huh.
Because you can filter light, right, of certain wavelengths.
Of course, astronomers do it all day long. We're going to be talking a lot about that. I've just never tried that before, and I wonder if I would notice a difference. Maybe I'll think about it.
Actually, it is very noticeable. It is, I can tell you.
Okay, all right. So
Mine's on for like $8.
say that, Mia.
What is it?
They're on Amazon for like $8. Like
Oh,
I got these for like $8.
Mia, do you find that they're helpful?
Yeah. There's
So-
different ones where they make everything seem yellow, and then there's other ones that like make them kind of like light blue.
But you're saying it keeps your eyes from getting tired when you have to look at a computer for a long time?
Yes.
Huh. It's funny. We spend so much of our, and like, think about it. When you're not on the computer in class, you're looking glued to this thing, right? Like, I grew up in an era where I wasn't glued to screens all the time. And it was kind of beautiful. Like, you thought more complex thoughts, conversations were more meaningful. But I'm just as guilty as the next person. I'm drooling all over this thing.
Yeah, I remember terrible memes like me following on 6 media pages to prevent any possibility of an actual thought occurring.
Right.
Kind of stuff.
Actually, a couple of my friends have been experimenting with like no phone, no social media, and they say, holy shit, you feel really good. Like, I want to be strong enough to wean myself off this thing at some point. But anyways.
Yeah. As soon as my phone breaks, I just buy a radio or a flip phone. That's it.
Yeah, maybe that's what we have to do to keep from going nuts, you know? Anyways, that aside, let's talk about the design of a basic refracting telescope. There's lots of different designs, but the type we're going to make is basically just a plastic tube, and there are 2 convex lenses. The one that gathers the light up at the top, that's called the objective lens. And the part that you look through is called the eyepiece. So you have an objective lens and an eyepiece. And let's get rid of the paper tube for a second so we can concentrate on what's going on. One of the reasons that we need to measure the focal lengths of these lenses today is there's a very particular distance that you have to set the eyepiece from the objective for your telescope to work. And it turns out that the distance between the 2 lenses is the so-called sum of the focal lengths. That is, if you add together the eyepiece focal length and the objective focal length, that's the distance that you set the 2 lenses to make a telescope. So what we're going to do today is I'm going to teach you how to measure the objective focal length. Then I'm going to teach you, we're going to measure an eyepiece focal length. And then we're going to use these holders. Let's make sure the audience can see this. I did hit record, right? Am I recording? Okay, I'm recording. We're going to put the lenses onto these holders, and we're going to separate it by the right distance on a meter stick. And then voila, we will have built a telescope and we'll peep on the neighbors, okay? So let's just analyze the optics of this. So these are called ray diagrams, and they kind of teach you what's going on, but it takes a little bit to understand this. So let's imagine that we were looking at the moon. When you look at distant astronomical objects, all the rays of light from a star or all the rays of light from the moon, they're basically all parallel to one another because they're so far away that only the parallel rays will actually strike Earth in your telescope. Now, parallel rays come into the objective lens, and they are brought to a focus at the focus point. Now, in our class today, or if you use a camera, what normally happens is you put your picture or you put your film or your screen right here. And if you put a screen right there, you'll actually make a little image of the thing that you're looking at. So you'll make an in-focus image of the moon. This is basically how a camera works. You have an objective lens, you put your film there, and it makes a nice in-focus image of the moon or the sun or whatever you're looking at. If you don't have a film there, the rays will just kind of pass through each other and they'll carry on their merry way and diverge. Now, if you take a second lens, the eyepiece, and you set its distance so that the focal length of the eyepiece is the distance from this point to the lens, what happens is the rays of light all exit the lens parallel again. Now, I want you guys to meditate on this for a second. Parallel rays come into the telescope. Parallel rays come out of the telescope. What did my telescope do for me? What's the purpose of this device?
Does it flip it the right way to see it? Does that make
Actually,
sense?
no, it will stay upside down. And this is an irritating part of looking through telescopes. One way I can demonstrate, Mariah, is let's use a green arrow up here. If this green arrow represents the top of the moon, it will be refracted down here, and the top of the moon will now be the bottom of the moon. For this reason, maps of the moon mapped out by astronomers are usually flipped upside down from the orientation on the sky. So unfortunately, you can do that, Mariah. You can add a third optical element to flip it again. But usually astronomers don't like to do that because every time you introduce another optical element, you reduce the quality of the light a bit. And we care more about the quality of the light than we do whether it's right side up or not. What's
So-
another purpose of a telescope?
So I think that the larger lens, it takes the parallel photons from a wider range and compresses them into a smaller range for your eyes to perceive. No, it doesn't
But
make
you're
sense.
not changing the wavelengths of light. These are optical telescopes.
I didn't mean that it compresses the wavelength. I meant that it just.
Yeah, what's the advantage of compressing the light? I'm trying to get you to flesh that out, Vladimir. What does compressing these rays do?
Okay, it doesn't make sense.
Well, it's actually kind of like what you said, but there's just one little part that you're missing.
Yeah,
Okay,
it's just I don't understand how exactly it zooms in.
okay, look. Okay, so this is what I wanted to talk about. You just said zooms in. You obviously do not change your distance between you and the moon. One of the telescopes have two goals. The first goal that everyone is focused on is magnification. And what magnification means is it means you're changing the angular size. People think of telescopes as it looks closer or it looks farther, but that's actually not what's happening, right? I can show you how telescopes do magnification. That's going to take a sec here. This is all a bit long-winded, but just put up with me. I know what I'm doing, okay? So if I wrote refractor magnification ray diagram, the way that refractors magnify things can be seen in a diagram like this one here, which will be the friendliest for you guys to look at. Maybe, would this be friendly? I'm trying to find a friendly image, not a scary. All right, that's not friendly. I just saw it a second ago. I like this one somewhat. Okay, so in this image, which attempts to explain how magnification works, I need to walk you through this. Let's say you were looking at a feature on the moon like a crater, and the angular size of that crater, maybe it's an arc minute or so, is given by this angle alpha here. Okay, so this is a feature on the moon like a crater. And what's going to happen, let me use my straight lines, is the angle comes and refracts through the focal length of the objective. And then it passes, can I put you guys at the bottom here? It passes through the eyepiece lens, and I want you to notice what's happened. This angle alpha, which was here, which was a smaller angle, let's call it 1 minute of arc, has now been magnified by increasing the angular size to 2 or 3 minutes of arc. So the crater appears larger to your eyeball because its angular size has been increased. Yes, this is one of the advantages of a telescope, is they can magnify, change the angular size. And if that's helpful if you're a pirate and you're trying to look at Vikings on the shore, you want to take a look at the Viking camp and see how many people you have to kill to get the treasure chest. I get that. Magnification's even useful in astronomy. Sometimes you want to zoom in on a crater or the Great Red Spot. But keep in mind, our class is about astrophysics, about stars and galaxies, right? For the purposes of stars and galaxies, magnification is actually kind of useless. The first reason is that stars are so small in their angular size that our best telescopes can't actually magnify them enough for us to actually see their surfaces. The other reason is when you actually start dealing with galaxies, you have the opposite problem. Let me show you a quick pic of the Andromeda Galaxy. The Andromeda Galaxy is maybe one of the most beautiful galaxies on the sky, and it's certainly one of the closest to us. Here's a beautiful image. Come on, internet. Go faster. How big do you think this thing is? I'm sorry, I don't mean big in terms of light years. I mean like the angular size of this galaxy is 3 degrees on your sky. And I need you to pause and think about that. Vladimir, remind the class, what's the angular size of the moon again?
Half a degree.
So how many times bigger than the full moon is this?
6.
6 times bigger than the full moon. Now, Vladimir, we can all see and resolve the moon perfectly with our naked eye, right? You can see
Yeah,
like
I never noticed an Andromeda Galaxy.
exactly. So now you're thinking the right question. If this is 6 times bigger than the full moon, why haven't you ever seen it before with your naked eye?
I don't know, maybe it depends on the hemisphere or the
No.
time.
You can see it
Maybe
from the
because the stars are scattered that I don't notice the whole picture.
Look, dude, you've noticed the moon before, even though it rises and sets. You just
Yeah.
look up and you're like, holy crap, there it is, right? How come we haven't looked up and said, holy crap, there's the Andromeda Galaxy?
The light is overwhelmed by the star.
It's not
No.
that Andromeda isn't big enough or magnified enough. It's that it's too dim. It's about brightness. See, your eyeball is kind of like a camera, and the camera speed, the shutter speed of your eyeball is a 60th of a second. Sorry, a 60th of a second. That's right. So every 1/60th of a second, your brain tries to capture photons and make an image. Andromeda is so dim on the sky that your eyeball can't capture enough photons in a 60th of a second to see it. This gets us back to your compression thing. Now try it again, buddy. Let's look at our ray diagram. What does our telescope do for us, Vladimir, when it compresses those rays?
It collects them over time. It collects the photons over time. So
But not over time, over area. Like, let's say
over area. Oh, because the area is much larger than the eye. Okay.
Right. If your eyeball was the size of this red circle, the eyeball might collect 2 rays per second from the moon, right? But if you Campbell soup condense them, now your eyeball can collect 1, 2, 3, 4, 5 rays per second. Basically, what you're doing with a telescope is you're increasing the surface area of your eye so that your eye can gather more photons. First and foremost, for astronomy, a telescope is a light bucket. It's a light bucket that's collecting photon raindrops from the sky. And this is why the best telescope is the telescope with the biggest objective lens. The bigger the diameter of your objective lens, the better your telescope. So this telescope is a sucky telescope because its diameter is like 3 inches. That other one that I showed you in the back there, its diameter is maybe 6 inches, so it's slightly better. Okay, now you've learned all I can teach you about telescopes. Let's build one. Won't take long, okay? All right, here's our setup. To do this portion, I need to, how do I do this? I'm trying to get all the preamble before I turn on the camera because you know I can only do it once, right? So let's just show you the optical setup we have here. I have a light source with a cardboard triangle. It's kind of blown out so you can't see it, but there's a little cardboard triangle. This lens holder is going to hold one of our 2 lenses. We're going to start with, this is the eyepiece, and this is the objective. Usually you want the objective to have a longer focal length, so I can tell this one's going to be longer. So this is going to be our objective. And here's me, just show and tell. I'm going to put it in the lens holder, okay? And I want you to kind of watch how I do this here. I also have a screen, which can make my image. I got to make sure these are kind of all aligned on the same optical axis. And I kind of enjoy this part of the setup for optics. Notice that I'm going to go through some great pains here to try to get my lens lined up decently with that cardboard triangle so that it's on the optical axis. And now what I can do is I can slide this thing. Oh, you know what's going on? This, I'm sorry guys, this lamp is too dim. I'm gonna burn my damn mitts off on this here. Okay, actually I've got the perfect thing for us to do. While that bulb cools down, I realized that I normally use a 100-watt bulb in the lab, and I grabbed a 40-watt bulb, not realizing that it wouldn't shine enough light to make a clear image. So let me explain on my whiteboard how this is going to work, okay? We have an optical bench, like so, okay? Now, over here, I have a holder that has a light bulb. Sorry about the crude drawing. And there's kind of like a cardboard triangle that looks like this taped in front of it. And this is basically going to be our source of light. This cardboard triangle, which I'm trying to shade in here, this is going to be the thing that we're going to make an image of. And what we're going to do is down here, we're going to have a screen, which is just a 3x5 index card. And the screen can slide back and forth on the optical bench. And then somewhere in the middle, we'll have our convex lens. Apologies for the quality of my lens. Okay, here's what's going to happen. Rays of light will leave the cardboard, top and bottom, and all in between. They will refract through the lens, and provided that we put the lens and the screen at the right distance, it will make an inverted image of the cardboard triangle, and we're going to try to move them around until they're in focus. We'll know that the image is in focus when it looks very sharp and crisp, and we can see a sharp definition of the shadow. If you slide this back and forth, it'll get fuzzy and out of focus. You guys probably know what that looks like if you use glasses, right? Let me define two distances here with a slightly different color. The distance, let me undo that. The distance, we're imaging this. The distance from the cardboard to the lens, that is going to be called S for source distance, okay? The distance from the lens to the screen, that will be called I for image distance. Okay. Our goal is to slide the lens back and forth until we make a very sharp and crisp focused image. We're going to measure the source distance S, the image distance I, and then what we can do is we can calculate the focal length of the lens using a legendary formula called the Lensmakers Formula. The focal length of your lens is, let's see if I can do this, source times the image distance divided by open parentheses source plus the image distance. And you're going to need to use the parentheses this time on your calculator to get the right value, okay? This is what is known in physics as the Lensmakers Formula. You might, sorry about the crude handwriting, but you might want to write that down. One last note to self here. S and I are intervals. You're going to see me go through a second here of trying to make sure that the cardboard triangle is as close to 0 centimeters as possible. And then let's say we've moved our lens to a distance where, let's say the lens is at 40.3 centimeters. And let's say our screen is at something like 70.5 centimeters. Can you guys tell me what S and I are in this case? This should be pretty simple if you know how to work on a number line. What is S?
40.3.
Sorry, Vladimir?
40.3.
Yeah, it's 40.3 minus 0 is 40.3. What is your I?
Like 30.2.
Yeah, you have to subtract this number from that number, and 70.5 minus 40.3 is 30.2. Okay, I just wanted to go over that process here. Okay, I'm going to pause the recording for 1 sec. I need to change this light bulb without burning myself for us to see, and then we will get on with the business. We're back, and we have light, thank heavens to Betsy. There was some high drama that you guys missed there, but all right. Now I can see my screen. Now we can do this dumb lab. All right. Let's take a look at the, I already explained the setup to you guys. You know what to do, right? Let's go to the phone, and let's try to take the measurements together. How are we doing on time, by the way? What's our time right now?
2:40.
Okay, that's fine. Usually a lab takes about an hour to do. We're gonna do this. This is gonna work, okay? Like I said, it's almost like the data collection part is so short that you guys might as well learn something while doing it. That's how I feel about it. Let's go to the iPhone and share and pray to Isaac Newton that this works. It looks like it's going to work. Thank you, Isaac Newton. Okay, and here we can see our setup. Okay, so this is the first time of me trying it with Joel's iPhone 7. Joel, if you're out there in the universe, thank you for your donation to Astronomy 1020. Here's my screen, here's my lens, and if I adjust the focus, you could probably see that cardboard triangle there. Let's see if I... All right. Let's slide the lens all the way. Ooh, whoa, did you guys see that? Ooh, look how sharp and crispy that image is. I've always loved, you know what's cool is when you get into like the upper levels of physics where you can study optics and stuff, it's just really awesome, really fun class. Okay, so I don't know how it looks on your camera there, but this looks pretty damn sharp and crispy to me. That's an in-focus image. Mariah, can you see how it's inverted? Because I think so, or Mia or Mariah, someone asked me about that.
Yeah, I can see it.
It's
Yeah.
upside down. The cardboard triangle is pointing down there. It's pointing up here. Okay, let's go to our lab page and let's just set things up here. Pencil. Oh, it's in my ear. Okay. All right. We have our name. This is lab number 7. Telescope design, but whatever. Put that on there so you don't forget which lab to submit it under. Of course, your section is AS1020. And, you know, whatever your damn section is, 01, 002, or 102. All right. Okay, now I kind of cribbed this from another lab sheet. Instead of orange, let's cross that out. We're going to name our lenses the way a telescope maker would. There's the objective lens. I'm just going to abbreviate it OBJ. Feel free to do the same. All right, there's your objective lens. And the blue lens will be our eyepiece, lens. All right, objective and eyepiece. We're not going to do this section because it's interesting but not directly helpful for telescopes. This section is going to be a different method of measuring the lens focal length. So let's change orange down here to objective, all right? The work is going to proceed so quickly that we're actually going to measure the focal lengths using 2 different methods. The first method will use the Lensmakers Formula for a nearby light source. And then I'm going to show you a cool method of doing it at infinity, but I'll explain that in a bit. For now, let's focus on our objective. We have S and I. This is sharply in focus. Why don't you guys see if you can take a reading to the nearest 10th. Wait, hold on. Can I do this sideways? All right. See if you guys can take a reading there. We want to go this time from the middle of the lens. So right from the 5 is where we should read things. Right from the center tick mark. What would you guys say the best reading is there? I know it's kind of dark.
53.4.
Yeah.
Yeah, 53.4.
I agree. So let's write down for S, 53.4. Now have your calculators handy because we might want to do a subtraction with our calculators. What would you say, once again, go from the middle of the tick holder right at the 5. See if I can focus that a little better. What do you think, guys?
$83.7.
Yeah, but you have to subtract that to get the interval, right? So in your calculators, have your calculator handy this whole time. Do 83. I'm sorry?
30.3.
Okay, so you did, let me just show the class what happened there. The coordinate was 83.7, but as we explained a moment, we have to subtract it from the lens to get the interval, minus 53.4. Did I do something wrong, or is that what you said, Vladimir? 30.
I should have said 30.3. Did I say 30.7?
Honestly, I'm going crazy now. 80.
No, it's 30.3. Yeah.
All right, it's 30.3. That's why
Yeah.
we have the calculator, right, Vladimir?
Yeah.
Okay, can I show you guys a real fast way to punch this in? But I want you to follow me and punch with me so that I want you guys to be my calculators, okay? I don't want to have to do this. That's your job. So remember our Lensmakers formula, okay? The Lensmaker formula goes, the focal length of your lens is S times I divided by S plus I, but we have to put that in parentheses for order of operations. So watch how quickly we can do this, okay? We'll do 53.4 times 30.3 divided by, open parenthesis, 53.4 plus 30.3, close parenthesis, and then equals. How many sig figs are we going to round to?
3.
Exactly. So what should we have for our focal length then, Vlad?
19.3.
All right, 19.3. The reason why we don't have to put units in our data table is because they've listed up here that all the units will be centimeters. So that saves us a little bit of time. Okay, now we want to do another trial because this could be fraught with random errors. So what we're going to do is I'm going to just move the screen back a little bit, and I want you to watch how it defocuses, okay? So I slide the screen back. You can see it gets fuzzy and out of focus. And then what I'll do is I'm going to slide this forward. Let's keep an eye on this. And let's see if we can figure out, ooh, damn. I actually like to slide forward a bit until it's fuzzy, back a bit until it's fuzzy, and that helps me figure out the center point. That's how I do a good focus. I kind of slide back and forth on as best as possible in the middle. All right, quickly, let's do our recordings again. Give me the S. Sorry, I'm trying to focus this here.
62.
Yeah, 662.
You
No.
can't.
60.2.
Oh, yeah.
Yeah,
Yeah.
what's wrong?
60.2.
2. Yeah.
That's 62. That is 60.2. Geez, guys. Hope you're not on my astronaut team. I don't want to crash into Mars. All right, 60.2. All right, and how about over here?
$89.3.
Okay,
Or
I'll go with it.
okay.
Let me just make sure do I have a, shit, it's dark in here, guys. Maybe I should, yeah, 89.2. Excellent, Tegan. Okay, but now you know what you have to do, right? We have to do 89.2 minus, you remember this, right? We have to get the interval, the distance between. How should I record that?
Wait, what?
What? What do you mean what?
What? It was 89.3, right?
Oh, was it 0.3?
Yeah. Wasn't it? Somebody
think,
said 89.3, and you said I'll go with it.
I think
Yeah.
it was 0.2 or
It's, well, look,
It's just it actually seemed to me like 89.25.
yeah, it's somewhere in between. So we only have to go to the nearest 1/10 of a centimeter. So we got to make a judgment call.
Round up or down.
You know what? We shouldn't split these hairs. We should pick a number and move on. Let's go with Tegan's original value of 80. I shouldn't have questioned her. 89.3. Okay. When I looked at it with my eyes, it looked a little different, but who cares? 89.3 minus 60.2 equals, all right, fine, 29.1. My only point before was we want to keep 3 sig figs, okay? Boy, that's a funny looking 2 that I made there. Okay. All right, so 29. So guys, compute the focal length for me while I relax and scratch my nose.
$19.6.
Okay. Can someone verify that I'm recording right now? Because I can't see the indicator.
Oh yeah, you are.
All right, once class I forgot to record, and I've just been paranoid ever since. 19.6 is pretty good. Let's do one more trial, okay? So we'll move it back even further. Make you fuzzy again. Get you sharp and in focus again. A little bit of experimentation. Okay, doesn't look like it's so much on the phone because it's blown out, but that's sharp. See how sharp and crisp that is? All right. All right, so best guess, what's the what's the measurement?
$65.3.
I agree. And then this is our coordinates that we have to get the image from.
$92.8.
Okay. So we do 92.8 minus 65.3, 27.5. Okay, guys, go ahead and calculate that focal length for me while I relax.
$19.4.
Okay. So we need to take the average of 19.3, 19.4, 19.6. So 19.3 plus 19.4 plus 19.6 equals, divided by 3, 19.4. That's our best estimate of the objective focal length. Now it's time to swap and do the eyepiece. I've got a lot of different lenses out here, so I was kind of grabbing them all in a hurry. I don't want to mix them up. Here's the eyepiece is a bit thicker. Usually the fatter lenses have a shorter focal length. All right, here's what's kind of cool about the eyepiece. Because the focal length is shorter, the image will be brighter, but at this distance, it's like really, really tiny. So tiny, you guys probably can't even really see it. What we can do is, because we're working with a shorter focal length, I can slide this lens a lot closer to my source, and I can bring this in. The image is smaller with the shorter focal length, but it's much brighter, which actually is unhelpful for the iPhone because this is messing up the contrast. I'm almost in focus here. Can you guys see that little bit of fuzz? You probably can't see that. There's a little bit of fuzz on the edge called coma, and that tells me that my system is not on a good optical axis. There we go. I can adjust this. Oh, sorry, you couldn't see that. I fixed some of the coma bits so I can get a nice, sharp, crispy image. Okay. Go ahead and give me my S distance, if you can read it. I don't want to lick. Hold on a sec, guys. Let me get the Windex, because I think part of the trouble here is that those things are quite dirty. I'm going to rub, I think from all the dry erase marker, there's, oh yeah, that's super helpful. All right. That ought to speed things up a bit. All right. So, guys, best estimate for S.
36.7.
Okay. Got a little Windex on your thing. And here,
$51.4.
okay. So we do 51.4 minus 36.7. 14.7. Can you guys confirm that I did that right?
Yes.
Go ahead and calculate the focal length. I'll save some time by resetting this up while you calculate the focal length.
I got 10.5.
Fine. Someone else verify that?
Yes.
Okay. This is a new config. Give me your next S.
$40.9. $54.4.
Okay. $13.5. Calculate the focal length, and I'll adjust the setup while you do it. We'll go back even a little more.
$10.1.
Same.
Okay. Next S.
42.9.
Okay.
$56.5.
Okay. So 56.5 minus 42.9, 13.6. That's weird. I was actually further away. That shows measurement slop. Do you see how when we went from here to here, the image got a little shorter? The fact that it's 13.6 is kind of goofy, but whatever. Calculate that focal length for me. That's the data we got.
10.3.
Okay. So can you guys tell me without a calculator, what is the average of 10.1, 10.3, and 10.5?
10.4?
Nope.
Oh.
1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. What is the average of this, this, and this?
10.3.
Yeah, it's gonna be right in the middle there. Sorry, I don't have enough hands here. Okay, at this point, if I wanted to, I could use these numbers and build my telescope. But I've got one last totally cool part to this exercise that I want to show you. So we don't need this middle section. But I want to explain something kind of cool about mathematics and optics and telescopes that's part of your learning lesson here. Okay, so we used the Lensmakers Formula. And we can use the Lensmakers Formula, especially when the source of light is a nearby source. What does nearby source mean? Well, consider your two focal lengths. Your objective focal length was close to 20 centimeters, and your eyepiece focal length was close to 10 centimeters. Nearby sources will be a few multiples of either 10 or 20. So anything 50 to 100 centimeters. And what really a nearby source means is this light object is close enough where not all rays are parallel, because I could have a ray from the top of the cardboard hit the bottom of the lens. In other words, this thing actually has some angular size in the field of view of the lens. But what if I was to image something really far away? Something like maybe those buildings on the other side of the street. Now, those things could be measured, the distance to them, but compared to the focal length of my lens, they're so many tens of thousands of centimeters away that source of light is pretty much at infinity. And something kind of cool happens to the mathematics when you let your source go infinitely larger than your image distance, okay? So our image distances are going to be 10, 20 centimeters, whatever. But let's imagine this goes to 10,000 or 100,000. And we can kind of cheat and we can say this source is going to be so huge that it's basically going to be infinity. Now I have infinity times I divided by infinity plus I. And you can actually work with infinity in mathematics. The rule is that any number plus infinity is infinity because you're just adding a teeny bit to a huge number. However, you don't do this with times because times is a higher order of business in a way, right? So this becomes infinity times I over basically what's approximately infinity. And weirdly enough, like they were two units in our dimensional analysis, the infinities cancel out and I get this funky equation, F equals I. You guys want to hypothesize what that means?
Oh, the focal length is approximately equal to the, what's I again?
What is I?
Uh,
It's the image.
so S for
S is
size and I for, oh yeah, I for image.
Oh, you know what? I forgot to calibrate this. That's okay. Okay. So calibrations are important. I should have calibrated to make sure that cardboard was as close to 0 as possible, but it's probably close enough. I is the image distance. And what this means is for a source that goes to infinity, the image distance when it's in focus is just simply the focal length. So this is another method to measure focal lengths, and I like to call this the infinity method. Now let me show you why it is cool, okay? So just give me 1 sec here. I'm going to bring my optical bench over carefully. I'm going to need a book. This 10-pound Resnick, Halliday, and Crane physics ought to do. Let me see if I can very carefully turn the computer because I know that you guys can't hear me too well. This will give you another view of what I'm doing, but the microphone will pick up my words. Okay. Okay, you guys can see there. Bitch is heavy. Okay. Let's prop it up a little bit so that we can see some distant buildings. That's not too bad a setup there. Let me just make sure you guys can see what's going on here. Actually, I think I had it good before. All right. Oh, there's going to be some nuttiness downtown. All right. So here's the screen. Here's the lens. The optical bench is staring out at downtown Providence. I'm going to swap out my lens, and we're going to start with our objective again. Oh, man. There's like a crazy bum fight going on up there. I really hope you guys can't hear that. Wow, some people are going nuts. Always an adventure down here, guys. Crazies never take a day off. You know, heroin never takes a day off, okay? They're always on the job. All right, so here. Anyways, here's my objective lens. And I really just have to show this to you guys because it's so cool. This is basically the principle behind how a camera obscura works, okay? And it's getting nice and sunny. So let's see if I can show this. Can you guys hear me okay? Audio okay? All right. I'm going to slide this Sorry, I need octopus hands to do this job. This is going to be dope. I can already tell. Whoa. Let's see if you guys can see this here. There's a lot of background light hitting this, but I'm going to adjust the shades in such a way that you're going to see what's going on here. Now, it's kind of faint. You can actually see it pretty well if you're in the room here with me. Oh, damn, that's tight. Okay, can you guys, whoop, let me adjust that. Let me get real close. Can you guys see that? That's the top of the Weston Tower. Isn't that so cool? And by the way, it looks pretty dim here because it's not super bright out today. That's in color too. You can see all of the colors of the tower. It's really beautiful. Like when I would do this at CCRI, when you could like see a green sunny day with trees blowing in the wind, it looks so magical watching birds go by. This is an art technique, guys. This isn't science anymore. This is how camera obscuras are done. Wait till you see the eyepiece. The eyepiece is going to blow your mind even more. But I just want to get you to look at that again because it's so darn cool. In fact, I can, oh yeah. Can you see that?
Yeah, I can see that more clearly.
It's pretty wild, right? Okay, so this means we have another method of measuring our focal length. So let's do this a couple of times. Can you guys do the subtractions for me because my calculator's not nearby? So we need to get our image distance, which is just this minus that, right? So let's take the big number first. I'm going to go into sideways mode because that's easier to read. Wait, are you good? Yeah, okay. What's the screen distance?
61.9.
And now subtract that from, that looks like 42.0. So do 61.9 minus 42.0. What do you get?
19.9.
Okay. So that's 19.9. Let's try to take another measurement as well. I suspect that it'll be a better focus or it'll be brighter if I want to go further back because one of the reasons it's hard for you to see is there's other light rays of white light bouncing off the cue card. So I'm going to slide that back a bit. Oh, yeah. I like to pick a feature, like I'm picking the top of the windows on the Weston Tower, and I'm trying to make sure they're really sharp and crispy. Or sometimes you can use branches of a tree. I'd say that's pretty good right there, okay? Oh yeah, look at that. It looks like a photograph. It is a photograph, right? That's how cameras work. Okay, what's your first measurement here, your first coordinate? Hold on, focusing. There we go.
69.
69.0 minus
49.1.
what's that give us?
19.9.
Yeah. Okay, you know what? I think 2 measurements is good because I've been taking a little bit of time here. Let's just average those and say for here, this will be our average. That's what I'm going to do, okay? The average is 19.9 centimeters, right? Let's swap it out and try the eyepiece. This ought to be kind of a fun trip. Remember, eyepieces have a smaller focal length, but the illuminance will be greater because you're concentrating the light in a smaller area. That's actually one of the rules about telescopes and lenses. If your lens has a focal length that's far away, your image will be huge, but it becomes weaker and diluted. When the focal length is short, you know what they call this? They call this the f-stop, or the speed of a camera. If any of you guys are photo buffs, you know the f-stop is like, it's the ratio of how much light you let into your focal length. We'll calculate that for our telescope in a minute. Okay. Here's the eyepiece, and let's watch what happens. Let me go sideways because that seems to be a little bit more dramatic. Oh my God, this is so cool. Those are clouds. You can see those big puffy clouds there. Let me focus this a little bit. Can you guys wait? Can you guys see that?
Yeah.
It's actually a pretty cool day to be doing this because you can actually see these. I don't want to sound like that orbital song, but these big white fluffy clouds. Look at that. That's so beautiful. I wish you were here to see it with your naked eye. It's really something. Okay, so let's get our first digit, our first coordinate.
$60.1.
Minus
49.4.
All right, subtract them up.
$10.7.
Once again, our image distance is just our focal length. I'm going to do this again. I'm going to slide it back a little bit.
Another thing so that could maybe help us see better. I don't know if that version of the iPhone does it, but if you click and you focus it and you see that square box with the sun, you can move your finger up and down and that'll change the lighting to better like focus on that.
Do you mean which? Oh, which box?
So like if you click on the screen that you like click on your phone screen, what you want to focus on, yeah, and you see the sun, if you just move your finger up and down.
Thank you. I didn't know how to use this iPhone because I still haven't. I still rock the iPhone. Oh wow, you're good. Okay, yeah. I think. Oh wait. It's moving very slowly for me, but that's a good point. That'll definitely come in handy in the future. How's that look? Is that any better? Or you know, it's when I was sliding it, it wasn't moving around too much. Anyways, you got the idea. I think that looks pretty good. I think we want better contrast, right? I don't know. Well, thanks for the tips there, Mariah. That's useful to know. Anyways,
Yeah, no problem.
What's this coordinate? Pick something.
63.9.
Minus, oops, sorry.
53.1-ish.
Yeah, all right. Subtract them up.
10.8.
All right. So the average of 10.7 and 10.8 is 10.75, but let's just keep it to 3 sig figs. We'll say 10.8. All right. Now for here, what we're going to do is we're going to take the averages of both methods. This is my objective, and this is my eyepiece, okay? So 19.4 and 19.9, what's that average? Is that 19.7? I think. 10.8 and 10.3.
It's like 10. What's 6? No. Yeah, I think.
Yeah, rounded up, it's 10.6.
Okay, nice. Okay, remember that these need to be separated by the sum of the focal lengths. You'll remember that from my earlier lecture. So let's add those together. 29, 30.3, right? Did I do that correct? Did I do that right?
Yeah, yeah.
All right. I just want to tell you, because once I make the telescope, we'll stop, but I want to do something with you first. Let's fill something else out. Because it relates to our class somewhat, let's think about what we've learned. The optical design is called a Keplerian refractor. Okay. The aperture is the diameter of our objective lens, and you can see it's about 5 centimeters. So our telescope is going to have a 5 centimeter aperture. Aperture just means the opening or diameter. This is an aperture right here. Okay. Remember, the diameter of a telescope tells you how much light bucket you have. Our focal length was 19.7? That's our objective focal length. Our eyepiece focal length is 10.6. Now, the focal ratio is what's called in photography the f-stop, or the f number. And it is the ratio of the focal length of the objective to the focal length of the diameter. We're pretty close to 20 centimeters, and 20 over 5 is 4. So the f-stop, and here's how we write this, is f4 optics. And I don't know why they put an f/4, but that's just how photographers do it, okay? Astronomers have to think about photography as well, because we take images of space. So our focal ratio is an f4 camera, or f4 optics. You can actually calculate the resolution using the diffraction limit formula from class. A class ago, you learned that the diffraction limit is 250,000 arc seconds times the wavelength divided by the diameter. Now, in for the wavelength, let's put optical wavelengths of 600 nanometers, or, maybe we'll just do 500 actually. 500 is green. I like to think of green as being in the middle of the visible spectrum. I hope I don't have to explain to you that these are optical-based telescopes, right? They use the visible wavelengths of light. The diameter is 5 centimeters, which in meters is 0.05 meters. So let's plug all that into our calculator here. 250,000 arc seconds times a wavelength of 500 nanometers divided by 0.05 meters. 2.5 arc seconds is the resolution. In theory, this should be much better than our eye. Our eye has a resolution of 60 arc minutes. 3 arc minutes. Let me try that again. Our eye can see down to 3 minutes of arc, so this should be roughly 60 times better than our eye. I don't care about the surface area, that's boring. The magnification is interesting. That's the objective focal length divided by the eyepiece focal length, which is approximately 20 divided by 10. So 20 centimeters over 10 centimeters. The magnification for this should be a factor of 2. So I just wanted to tell you some things about this telescope. I wanted to tell you that it's an f4 telescope. It can see down to about 3 arc seconds resolution, and it has a 2 times magnification. Now let's build it, and we'll call it quits with this day and take spring break. Okay, so what I need right now is I need a meter stick.
Did anybody else have a chance to copy the alpha minimum equals something? Just 250,000.
Does that help?
I think it's lambda over d. Okay, 0.05 meters. Okay. All right, thank you.
Yep. So what I'm doing is I'm putting my lenses into some holders that can slide along here. Okay. Let's build a telescope together. Now I'm going to set the eyepiece to 20 centimeters. So I'm currently at 20.0 centimeters. How far away should I put my objective? I don't know if you guys can hear me. How far away should I put my objective? here's a hint.
30.3 centimeters.
But careful, Mariah, 30.3 centimeters away from 20 centimeters. It's an interval, right?
Okay, yeah.
So where should I put this bad boy?
50.3.
50.3, right? And I'm going to make a slight adjustment to account for errors. Oh, shit. No, wow, we're good. No adjustment needed. That was perfect. You guys did an excellent job. You ready to use our telescope? Okay, let's do some peeping on the neighborhood. Let's see if I can do this here. I've got to get my exit pupil right. Ooh.
So that magnifies better, doesn't it?
Yeah, hold on. This itself is a lens, so I have to, let's look at that Weston Tower together. There's a lot going on here right now with my, apologies. Wait, okay, with my eye, it looks damn sharp. It looks really nice. Let me see if, I just got to get the exit pupil of this camera right. This is not as easy to do as you think it is, but oh, there we go. What do you think?
That's so crazy to see. It's like perfect.
So
Damn, that was a sharp one.
Right?
I
Really
keep
nice.
thinking of the house from Up, just in the sky.
Huh?
I keep thinking of the house from Up, the movie, when it's in the sky, just minus the balloons, because I can just see all the blue.
Let's see what the Inverts up to. Oh. Sorry, it's hard to hold all this steady. Oh, yummy, Korean food. Okay. Anyways, I hope you enjoyed building a telescope with me. That was a fun little lab. I think a nice way to tee us off for spring break, right? Cool. Sorry that went a little longer than I expected, but you know, it's still, yes, Kiana. Let me see if I can do that. You guys are going to turn in 2 pages. Of course, you're going to turn in this, right? I don't know, Kiana, when you say, can I see paper again? I don't know which paper you mean, because there's 2. But let me, hold on a sec. Let me readjust to a more comfortable position to talk to you guys. Okay. We're going to turn in 2 papers, if that's okay with you guys. I don't know if my iPhone will work again. So one of them is, let me go to a full screen for those watching the video later. They're sort of stuck with my view. Okay, yeah, I hear you, Kiana. Let's just take a look. So here's the data from the first page, okay? Here's the data from the second page. Sorry, the focus isn't great with this webcam. Okay, so that takes care of Kiana. Don't forget to submit this to Lab 7. Tegan, don't you forget on me now.
Hi. Yeah, I have some questions about just something about my grades. Would you rather have me email you or?
No, why don't I'll stop the recording and then everyone else who wants can leave and we can just hash it out in person. Does that sound good? Or
Okay,
like this, okay?
that sounds good.
Vladimir, if you're cool with Vladimir sticking around, I wanted to talk to him about something as well. Hold on a sec. So I'm going to stop the recording now. To everyone watching the video at home, have a great spring break. No class next week. The week after that, which is the next time I'll see you guys is Tuesday, the 16th of March. Okay. We'll be coming up on the spring equinox. So get in the mood for sunshine. And I will see you guys after spring break.